In this demo, I'm going to use the software EPANET to determine the flow rate through each pipe and the pressure at each junction in the network that's shown on the screen. And this is the second part of a two-part series where I solved this same network using some calculations with Microsoft Excel and the Hardy-Cross method. And so I'll give you a link to that earlier demo in case you haven't already seen that. So now I'm going to solve it with EPANET. And first, just a warning, I'm not a power user of EPANET. I've only been using the program for a couple of days, and this is probably only the fourth time that I've actually even started it. So I probably don't do things in the most efficient way or as quickly as you could if you have a little more experience and training. But I'll see if we can find the same flow rates and pressures using this method as was demonstrated in the previous Excel solution. So the first thing I want to do is I want to change the units to SI. You can see that we've started off in gallons per minute. So I'm going to change the analysis options so that instead of gallons per minute, that now it's liters per second. And by doing that, it set all of the units, whether it's length of the pipe or diameter of the pipe, the demand, all of it is now in SI units because I changed that flow units. The other adjustment I'm going to make is to the head loss formula because now it's set to use the Hazen-Williams equation, and I prefer the improved accuracy of the Darcy-Weisbach equation, and so I've made that change now. With those adjustments made, I'm going to begin drawing the network using these tools across the top. And so I'll begin with a reservoir and drop a reservoir on the screen. Where doesn't matter so much. I'm not going to use any kind of scaled lengths. I'll be entering user-defined lengths for all of the network characteristics. Next I'll have a junction, and this is going to be the junction A. Here is B, C, D, F, and E. All right, so those are all defined, and now I'm going to connect the dots by adding pipes between them. And so this is the pipe between the reservoir and junction A, pipe from A to B, from B to C, from C to D, D to F, and I am trying to be precise with this because if you click in the wrong spot, I think it won't connect the pipes like we'd want them to be. And finally from F to E, oh, I also need to do E to C. All right, so we're connected. Next, I'm going to add some annotations just for my own convenience. I'm going to add these labels across the top, and so this is junction A. This is junction B. Now, this isn't changing what the system refers to as these junctions. This is just for my own visual reference, and I'll go in and change the system labels for each of those junctions in just a moment. F and E. All right, so now let's do that thing and change the junction names. And so if you click on junctions down here in this browser, it will bring up what the system is calling them. And for instance, what I know is junction A, it's calling junction 2. And so let me first of all change its ID to A. And then the other thing I'd like to define for that junction is how much water is coming out. So what's the demand? And also the known elevation of the ground at that location. And so junction A has an elevation of 0 meters and a demand of 0 because there's no flow coming out at A. Here, what the system is calling junction 3, I want it to be calling it B. And the elevation of B is 9.4 meters, and the demand there is 350 liters per second. All right, moving on now to what it calls for. I'm going to relabel it as C, and C has an elevation of 19.2 and a demand of 0. There's no flow coming out of the network at C. Junction 5 is what I want it to know as D. The elevation at D, 25.2, and the demand is 100 liters per second. Junction 6 is F, elevation 5.5, demand 50 liters per second. And lastly, we want to relabel 7 as E, and that is where we have an elevation of 2.1, and the demand there is 450 liters per second. So we have defined where the outflows are and how much, and the system will automatically draw that flow from the reservoir. So I don't have to tell it how much should come out of the reservoir, because it will apply continuity to calculate the outflow through this pipe required to feed all of those locations in the network. Okay, so I've defined all the data that's needed for the junctions. Let's now move on to the pipes, and we'll do the same thing where we change the name of the pipes to label it, for instance, this pipe that it's calling pipe 2, I want that to be AB. And then I'm also going to put in the length and the diameter. And I've changed the unit systems over, and so it's going to be looking for the length in meters and the diameter in millimeters. So this pipe AB has a length of 220 meters and a diameter of 400 millimeters. Roughness, I need to change all of the pipes because I'm using the Darcy-Weisbach equation for friction loss. 100 would be fine as a C value if you're using the Hazen-Williams equation for head loss, but since I'm using the Darcy-Weisbach, what it's asking me for there is the equivalent sand roughness, epsilon. So that's 0.3, and we've defined the roughness, length, and diameter for pipe AB. Let's move on now to BC, and BC has a length of 100, a diameter of 200, and a roughness of 0.3. Pipe 4 is CD, a length of 80, a diameter of 150, and the roughness is 0.3. DF has length of 200, diameter 300, roughness 0.3. This is pipe AF, length 180, diameter 300, roughness 0.3. Pipe 7 is EF, length 80, diameter 250, and roughness 0.3. And finally, pipe CE has a length of 150 meters, a diameter of 350, and the roughness of 0.3. Okay, so we've defined the characteristics of the pipes. Next, I just need to tell it how high the water level is in that reservoir. So if I go over here to the reservoir table, or if you just simply double click on an element, then it'll bring up that same table. So reservoir 1 has a total head of 65 meters. Next, I'm going to click on the Run button. All right, so I've got a little warning message, and I figured out what the issue is. I never defined the characteristics of this pipe that connects the reservoir to junction A. It's assuming it's only 12 millimeters in diameter, so there's going to be loads and loads of head loss through that. So what I had put on this example is, let's assume that the length is 10 meters, and here I've written diameter as 1,000. I meant millimeters. The point is, I want it to be a really big pipe so that there isn't any loss through that pipe. So 1,000 millimeters, and the roughness is 0.3. Let me just 0.3. I don't know if it matters either way, but okay, so now I've put the characteristics of that pipe in and execute the model. This time it's successful without any warnings. Now, the flow through this pipe from the reservoir to A is 950, and that's what we'd expect it to be because all of the cumulative outflows inside of the network are 950. Now as for the rest, we're going to compare it to the answer, the result from our previous spreadsheet solution. So let's take a look at that. Here are the flow rates that I got using the spreadsheet solution. So for instance, the known flow rate through pipe AB is 528. So now here, using EPANET, if I click on AB, it's telling me the flow is 528.11 is the flow rate. So that's accurate to within, here it was 0.1. So that's accurate to with as much precision as we need it, certainly. Less than 0.1% difference between them. So let's check pipe BC. It's saying for pipe BC that the flow rate is 178. So here's 178. CD, flow rate 37.7. CD 38. That rounds up, so it works. DF 138 effectively. Here's the 138 for DF, and of course the minus here means the same thing that it does in the spreadsheet. It means anti-clockwise, and so the minus flow rate just means it's the opposite of the clockwise direction. So far so good. AF, our calculation from before was that pipe would have a flow of 422, and it's saying the same here, 422, the minus sign because it's anti-clockwise. And EF 234 liters per second, 234. All right, great. So the flow rates match up. Now we want to compare it to the pressures. In this spreadsheet that I did before, I had calculated the pressure at each of the junctions, both in terms of kPa and in terms of pressure head, because that's how EPANET describes things. And here is each of the junctions. I calculated the total head and the elevation and used that to determine the pressure head for each location. So now if I go to the junction table, junction A should have a total head of 65 meters because there's essentially no head loss through this first pipe. That's good, it matches up. B, we expect it to have a pressure head of 46.38. So 55.78 is its total head, but then you subtract out the elevation to get the pressure head. And so here, what it's calling pressure is pressure head. So that is meters of water. And if you need to know the pressure in kPa, then you multiply this by 9.81. So check, that works. Junction C, 18.55. Junction D, 15.5. Junction F, 37.8. And junction E, 33.5. So I feel pretty good about this. EPANET has got all the same flow rates, all the same pressures. It seems to work. It's a free program available online, no activation needed, no license tool, no connection client running in your system tray constantly. It's not the most fancy software by any stretch, but it'll do what it needs, what you need it to do if you're trying to understand the relationship between flow rate and diameter. So let's say if I wanted to make some optimizations to this network, like if I was allowed to have, well, these pressures dip pretty low. Look at these pressures are below 240 kilopascals, which they shouldn't be. So if I wanted to try and optimize this network, that tells me that the pipes that are feeding junction C and D need to be upsized. They need to be a little bit larger because right now the network is too small if I was using 240 kilopascals as my criteria. So if we just scoot over here and look at which pipe is feeding junction C, the flow is coming through BC. So if I wanted to make an adjustment, then I could go over to the pipe table. BC right now has a diameter of 200 millimeters. Let's see if 250 millimeters makes a difference. All right, so that's going to give me more pressure at C. And my other problem area, according to this, was what about junction D? So the flow to feed junction D is coming through DF. So let's also upsize DF a little bit. So here's DF, and right now that diameter is 300. Let's make it 400. All right, so I've made 2 adjustments to the pipe diameter. I'm going to click this Run button, and now I can switch back over to the junction and find out what are my 2 problem areas were C and D, because the pressure was too low there if we were using 240 kilopascals as kind of a lower limit. So now at, let's scroll down a bit. All right, so now at junction D, how much pressure do I have now? 22 meters of pressure head. And if you multiply that by 9.81 to find out the pressure, so 22 multiplied by 9.81, that's still only 215 kilopascals. And so it's an improvement. I've got more pressure there than I did before, but still maybe not quite enough. So I need to upsize the pipe that's feeding junction D a little bit more. And let's look at the situation at node C. At C, my pressure now is 26 meters of head times 9.81. So the pressure there is 255, which is good. So I don't need to upsize the pipe that feeds junction C anymore. So it looks like my change to BC is sufficient, but I need to make a further upgrade to DF. So you get an idea of how this would roll. We basically just keep making changes to pipe sizes and looking for what is the bare minimum diameter that gives us an acceptable pressure at each location in the network. So let me recalculate, and then my problem area was junction D, so I'll open up junction D again, and now the pressure is 22.33 kilopascals, and so 22.33 multiplied by 9.81. Now I've got 219. You know, we're real in trouble here at junction D, and maybe the issue is just that elevation, right? Like it's so high that we're not going to have a lot of pressure there because its elevation is so high. So we're going to have to keep making that pipe progressively larger and larger. But anyways, the point of this demo was really just to show you real rough and quick how you can use EPANET to solve a pipe network. Hopefully mission accomplished on that. So good luck on your projects, and as always, let me know if you've got any questions.